Then hey, hi everyone. Good afternoon. Hey, hi. Hi, good afternoon. Just checking the. Yeah, how many of you have taken this puzzle? Not many. Quiz 10. What happened, friends? Facebook is better than LinkedIn. Not good, not good. Keep pushing you people and you don't respond. Keep pushing, not responding. Keep pushing, not responding. Participate here, guys. Learn the concepts, learn the questions. Are these questions so easy? Still waiting for a few more people to join in. Day 11. Okay, let's begin the session. This is what we've discussed. Keep on detail here. So you're talking about R programming, right? So when you talk about R programming, we need to look at the capabilities of R. It's a functional oriented programming language. It's an open source. It's open source, functional oriented, right? It is free, open source and free, of course. It's a high level English-like language, and it is an interpreted and interactive programming. Interpreted and interactive programming language. It's developed for statistical computing, and it has very easy syntax to write the programs. And because in R console you not have many user-friendly options, we go with this IDE, which is interactive development environment, which is provided by, of course, which is supported by RStudio. Right, RStudio itself, I mean, this is the organization which gives us this ID. And this has a lot of additional nice user interfaces which helps the programmers to write the code in a very easy and interactive way. We discussed about the variables. Of course, we discussed about RStudio, the panes and all that. Then we discussed about variables. Variables are nothing but memory items. And we use standard format or properties to define the variables, right? And as part of this, we basically learned that the variables cannot have numbers at the beginning. Text in R is English-like text, so it understands uppercase and lowercase as two different letters. It's case sensitive. And the index starts from 1. And for variables, we can simply assign the values using assignment operators, either equal to or arrows. Most preferred is this. Next. When we are assigning the variables, we have to look at the variables from English perspective. So you cannot have special characters, spaces also. The only special characters which are allowed is dot and underscore. That's it. Right? So that's your variables in R. Then we discussed about the data types. And the data types are integer. Then you can see double, which will be represented as numeric values in R. Then we have character types, date types. Then you also have binary types, there's Boolean, and then complex. Then the structures, data structures that we have discussed, it all begins with vector. R understands vectors as the least granular sequential data. Atomic numbers are there, right? Standalone atomic numbers can be identified, but when we talk about structures, then we'll talk about dimensions, right? So one-dimensional sequential data is vector. It can also be converted into a list. The difference is only one data type. Here you'll have multiple data types. Then we can also convert the data vector into a two-dimensional arrangement, a two-dimensional structure using matrix. Matrices can be created using this matrix function. Then we have a multi-dimensional data in the form of arrays. Then the special format structures, right? The special format of data is factors. It's categorical data which will be represented in numeric scale in the statistical programming language called R. So internally, the data which is non-numeric will be measured on a numeric scale using levels. Then to have a proper structure to the data in R, the standard structure is defined as data frame, which is nothing but the table, right? And this is the default data abstraction, which gives us tables. In tables, we have rows, which basically are nothing but collection of columns. So that's about your data structures. Then we talked about functions. What is the syntax of functions, friends? Do you remember the syntax of functions? Every programming language has these functions. And these functions can be broadly classified as built-in functions and user-defined functions. So user-defined function, what is the syntax? Anyone? You guys remember? Nobody. Not even one. Why? What happened, friends? Forgot? What is the syntax that we use here to create program? The function name. Yeah, what is that? So we put name of the function, then we use this keyword called function, and then we put flower brackets and end it with flower bracket. So the body of the custom function will be written inside the flower brackets. This is the syntax. You forgot, everyone. 2 days, Saturday and Sunday, boom, gone. You become Gajnis. Yeah? This is the custom function syntax. Next. We also discussed about operations on the data, and here we did arithmetic operations, the very basic arithmetic operations, plus, minus, multiplication, division, right? These things. Then we've also discussed about logical operations, then we discussed about relational operations and special operations. Then extending the functions, the discussion went to packages. Packages are basically the collection of multiple functions. Along with the functions, packages may also include data sets, sample data, along with functions. We are saying functions, not one function, but multiple functions. Then sample data will also be there, and you'll also have documentation. Collection of all this is known as a package. How do we get a package? What is a function? R code to get a package? Let's see how many of you all answer that question. No one? No, it's not library. Library is also there, but that's not the only function that we use. What is the other one? Yeah, YouTube. Nobody's answering there also. Close. Yep. Ah, that's right. That's right, Balakrishna. Not installed. Installed means it will give you the list of packages which are already installed. It's right there on the screen. You're not seeing the screen. Install.packages. Or we can also use the front-end option, the graphical interface. Right? But yeah, either one you do. The code which gets executed is install.packages. And very importantly, the package name should be mentioned in the double quotes. That's mandatory. Once you install the package, then to invoke it, to use this package, we use library. Library is a session-specific function, right? We will be calling library of the package in order to start using the package in particular sessions that we are executing the code. Right? That's about your packages. Then we've also discussed about if conditions, conditional statements, if else, nested if, right? Those conditions. Then we discussed about the loops, pre-loops, post-loops, infinite loops are finite loops. Infinite loops basically are while loops, generally. It's not that you will always have to go with that. I mean, it's not defined that way, but practice that we do, right? While loops are generally going into an infinite looping condition. That means when you're writing a while loop, the loop will repeat itself iteratively. It is executing the code until the condition is satisfied. How many times it will iterate? There's no risk to that. Yeah, that is not fixed. Right? That's not fixed. But if you look into a for loop will repeat itself to check the conditions for a finite number of times. Right? How many times you might want to verify for the condition is upfront fixed. Hence, we call it as a finite loop. You can also write while loop in that way. Right? But while loop can generally go infinite loops, right? Infinitely it is repeating itself. So that is about finite loops and infinite loops. Then we also have repeat loops, which basically want to write a custom code. Right? You might want to write a custom code where you are going to say repeat the steps multiple times until you apply a break function. That's a special kind of a function or a loop condition that we have. Repeat. Then we have break function, we have switch function. Switch is going to jump from a specific location directly to a value that we want to jump the code, or jump the line. Condition, the control of the console, control of the code will be moving from line 1 to line X if you use switch function. If a condition is satisfied, then do a specific task. You're going to say go to that line. Right? So switch is used for that. These are certain functions that we discussed. Now, post that, we've started to understand how this programming language is actually helping us to analyze the data. And this is where you people were exposed to a project management methodology. What is that? What is that? What is a project management methodology, friends? Nobody is answering again. Come on. Any data analysis project will have to generally go with this CRISP DM methodology. Right? And in CRISP DM methodology, we have 6 different stages or phases of the project. And first and foremost step is to understand the business problem. I'm asking you to do something. What is that something? You need to understand that clearly, right? So understanding the business problem is very important, right? Otherwise, you know what happens. Your wife will beat you if you're married, if you're not doing the right things, right? So doing the right thing will start from understanding that thing that you need to do. Now, as part of business understanding, we will look into the objectives that we have to solve. There will be a number of different objects. What is that important object? What is the primary problem that client has? You have to solve that. You have to address that. So you record it. But when you're trying to address this, there will be certain conditions that you have to make sure you are meeting. And that is constraints or conditions that you have to look at. Right? So you have to document the objectives, you have to document your constraints. Documentation is another very important point. If you do not document and if you feel that your client is going to stay with his word, then forget about it. He will have his versions changed. Right? So documentation is very important. Next, once you understand the business problem, you have to classify the business problem into one of the 4 stages that we have learned. What are those 4 stages? Let's see who will answer this question. There are 4 stages of analytics. What are those 4 stages? Yeah, YouTube. Folks at YouTube also, please participate. Very good. Yeah, Padma. Very good. Prescriptive. Okay. Why only one person responding? Okay, now I got the responses. Mallikarjuna Rao, very good. Very good. Fani Kumar, yeah. Kumari, sorry. Fani Kumari, very good. So there are 4 stages, right? These 4 stages are descriptive, diagnostic, predictive, prescriptive. Descriptive and diagnostic are looking into the past, right? They look into the historical data and then help us understand what happened till now. Now, using this knowledge, we will try to identify the pattern, that is doing predictive analytics from the understanding that we have from the data by performing descriptive and diagnostic. By understanding that pattern, we will try to predict, right, using that pattern. Now, from this knowledge, from your descriptive, diagnostic, predictive analytics knowledge, we will further apply strategies. Prescriptive analytics is all about prescribing solutions, right? So these are the 4 stages that we discussed. Next, we've understood the importance of the data. Now, everything that we are doing here is depending on data. If you do not have the right data, you cannot perform any analytics. Data is the new oil, right? So we collect the data from various sources. We have primary source and secondary source. We collect the data from these sources and then start looking into the data. This is called as data collection and data understanding. When I say data understanding, remember, you have to map the data features that you're collecting to the business problems that we have understood in the first stage. It has to be mapped. Right? Now, once we map it, you'll also try and understand that there are few things which are missing. Right? Probably there are few things which are given unnecessarily. You might want to ignore those features. Right? So understand the business condition, map it to the data that you have collected. This will help us to basically do pre-processing on the data. And as an analyst, as a data scientist or a data analyst, the majority of the effort that you will put in will be in working with data. When I say working with data, the raw data that you're receiving has to be pre-processed and prepared so that you use it for further analysis. Statistical mathematical concepts that you are applying, right? So for those, you will have to use these, for applying those mathematical or statistical computations, your data should be in a specific format, isn't it? So we are data, right? Majority of the effort will be going in this. More than 60%. of your entire effort will be here only. So you are understanding whether the data that you have collected is numeric format or non-numeric format, whether it is a big data or whether it is a regular data, right? You're also trying to understand whether the data is balanced, imbalanced, whether it is live data or is it already recorded and stored somewhere. All these things. And then once we collect the data, we also do statistical calculations, right? We call them as descriptive statistics. We calculate the first thing on the data to understand the characteristics of the entire data set. That would be the first computation that you do. And that computation is called as measures of central tendency. And what all calculations we do here? What calculations do we here? Measures of central tendency. Mean, median, mode. Very good. Mean is the primary calculation that we do. The statistical calculation to represent the characteristics of the data is mean. But what is the problem with the mean? The problem with the mean is that it is getting affected by outliers. What is outlier? What is an outlier, friends? Outlier is an extreme value which is not following the pattern of the data, which does not resemble majority of the data, exceptional cases. So we need to identify these exceptional cases and act accordingly. When you have outlier, we'll act accordingly. And here we will be trying to do outlier treatment, which basically is the 3R rule. The 3R rule is remove, or I should start with the 3R's rule is followed for outlier treatment. The first one would be rectify. You are correcting if there is any mistake in the entry. That could lead to, right? Data entry issue could lead to an extreme value. So you're correcting it. Then we have, after rectify, we have retain. You keep that outlier and then proceed with your calculations. Or we remove. Rectify, retain, or remove. These are the 3R rule that we follow to treat an outlier. Right? Either you nullify the outlier by applying Winsorization technique, or we remove the outliers by trimming technique. Now, if you have to retain your outliers and then proceed further in analyzing the data, then you will further decide on should we separate the outlier data from the regular data. Maybe, yeah, you might have to separate your data from your regular data, right? Outliers might be separated. And then you are applying your analysis separately on outlier data and regular data, and finally you will map the results. So different things will come into picture when you are dealing with outlier data. Then we also have to understand the spread of the data, not just mean, median, mode. It's not just the concentration of the data that we have to look at, but we also have to look at spread of the data, isn't it? That spread of the data is measured as average spread, and here we have variance, standard deviation, and of course range. These calculations are known as measures of dispersion, spread of the data. But this spread, remember, is measured on an average spread with respect to the center. Then we've also looked at the shape of the spread. Fine, spread of the data is there. On an average, from the center, data is spreading by so much. But which side it is more? If I take center, whether the data is spread more on the right side of the center or left side of the center, that is given by skewness, which is the third moment business decision, and it is having negative skewed or positive skewed measures. Then we have kurtosis, which basically represent the sharpness in the distribution of the data. Sharpness, peakness. If the spread of the data with respect to the center is less, that means more data is lying at the center, then we will be getting a very, very sharp peak. Whereas, if we have very, very wide spread, I mean the data is not close to center, they are widely spread across the center. That means you have a high variance. If that is the case, then we get a wider peak. And here we have the terms mesokurtic, platykurtic, and leptokurtic. You might want to praise your girlfriend. You say, hey, wow, you look platykurtic today. What does that mean? Yeah, I always praise my wife, saying, hey, wow, wonderful, you look so wonderful today. You are platykurtic today. What does that mean? Yeah, my wife did not understood that terminology, so I'm saved. My wife don't know the terminology, right? That's the reason I use that word, platykurtic, which basically means wide. So your peak will be like this, wider, right? Now, if your girlfriend or your wife understands the terminology, then you are gone case, right? Leptokurtic basically means a sharp peak. Okay? You might want to remember the terminologies like this. Just comment once on your girlfriend, and yeah, you'll never forget. So these are your shape statistics. Skewness and kurtosis, they are known as the shape statistics because they are talking about the shape of the distribution of the data. And how do I interpret the shape? We interpret the shape by visually inspecting the data, right? So we've also done visualizations in R, and the visualizations that we did are bar plot, we did line chart, we did pie diagram. In fact, we also did 3D pie. Then we did dot chart. We did histogram. And for this skewness and kurtosis, histograms are preferred. Then we also did the most popular visualization technique, box plot, because this also shows outliers explicitly. What is the formula that box plot uses to identify outliers? Anyone? Anyone? No. For what? Guys, come on. formula which box plot uses to identify outliers. Q plus or minus 1.2 IQR. What is IQR? IQR is Q1 minus Q3 or Q3 minus Q1. So this is your box plot. This is your Q1. This is your Q3. So we are measuring the box portion and saying 1.5 times of this box portion should be in the whisker. If your data are falling here, then they are not treated as outlier. But if the data is beyond this calculation, either this side or this side, then we treat it as outlier. Right? This is what we discussed. Interquartile range. Very good. Now today, we will be looking into something called as a density plot, something called as QQ plot, something called as normal distribution. Okay, interesting things, interesting things. All right, so let us look into probability to start with. What is probability, friends? Yeah, what does probability actually mean? Chance of an event occurrence. Very good. So probability is nothing but interested events by total number of events. So let me reduce all this. We'll come here. So probability is nothing but interested events by total events. If I flip a coin, then what all possible values do I have? If I'm flipping a coin, what all possible values do I have? Either heads or tails, right? Assuming the coin does not land vertically, these are the two options that I have. Now, when you are flipping the coin, what is the chance that you end up getting heads? How many heads are there in this possible outcome list? Only one head. Out of how many possible values that you might end up getting? 2. So probability is 1 by 2. Interested events by total events. I'm going very, very slow. People who are already familiar with this, please, I request you to hold on, because we have friends who might have forgotten these concepts, right? So you have to respect them as well. Now I am rolling a die, a single die. What are possible outcomes do I have? 1, 2, 3, 4, 5, 6. 6 possible outcomes are there, right? So if I say probability, we will say number of interested events by total. So total events, you're experimenting. What experiment you're rolling the die? Then what are the possible values you might end up getting? 6 possible values are there. But within these 6 possible outcomes, you want to learn what are the chances that you have to get 1. How many values are there? 1 is only repeated once. So my interested event is 1 by total, which is 6. 1 by 6 is the probability or chance that you end up getting 1 by 6. Sorry, 1. Now, what is the chance that I might end up getting, let's say, 2? What is the chance that I have to get 2 when I'm rolling the die? Okay, good. Yeah, I was just checking if anybody says 2 by 6. So the answer is 1 by 6 only. Why? Because 2 is there only once there in that list, right? 2 is repeated only once. So number of desired equations, number of desired values out of all the values, the total values. So result is 1 by 6. Now let's discuss properties of probability. Okay, very, very important. There are 2 properties of probability that you have to revise. Can anyone tell me the properties? What are the properties? Yeah, anyone? Nobody. Okay, the first property is the probability, which is the chance of the event or a specific value, will always lie between 0 to 1. Yep, this is the first probability that you need to look at. It cannot be, probability cannot be less than 0. The last value it can take is 0. That means when you are rolling a die, for example, and if you say the probability of you getting 1 is 0, that means you roll the die n number of times, infinite number of times, and you never get 1. Right? And if I say the probability can max take 1, that is 100%, basically means when you're rolling a die and you say the probability of you getting 6 is 1, that means infinite times you roll the die will always give you 6 as an output. It doesn't give any other result. Right? So this is the range of the probability values from 0% to 100%. Right? That's all your probabilities can take. Then the second property, sum of all the probability values, it will always be equal to what? 1. It will always be equal to 1. So for an experiment, you know there will be an outcome. For sure you know the outcome. That means there is a chance, 100% chance that there will be output. Right? But what is the chance for each value? We don't know. So we are calculating that by interested events of your experiment out of the total events. Right? Desired chances by total chances. So when you add all those interested events, then it will be nothing but total number of events, right? So the summation of all the properties will give you result 1. Very, 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 very important properties, and these are something that you should not forget even after your death. Right? Very important. All right. So we discussed about probabilities. Now there is something called as conditional probability. Let's talk about it briefly. We're not going into details. let's say I have a jar. Okay, this is a jar, and I have put, let's say, chocolates in it. I have a 6-year-old son, right? For him, I have put some chocolates in this. Okay, red color and blue color chocolates. Assume. Okay, so let me give you the numbers here. The chocolates, the red color chocolates, let's say, are 10. The blue color chocolates are also 10. So total chocolates, how many chocolates are there here in this jar? 20 chocolates. Okay. Now I give this jar, I put this jar in front of my son. I ask him to pick one chocolate. Pick one chocolate. What is the chance that he ends up picking a red chocolate? So I will determine this as X being equal to red. Yeah. Very good. Yeah, only Priyanka has responded. What about others, guys? Come on. You have to be quick in answering. Very good, very good. So the answer is 10 chocolates out of 20. Isn't it? Because you have 20 chocolates. My son can pick any one among those 20. But what is the condition that I'm looking at? What is the interest that I have in? I want to see the chance that he ends up getting a red chocolate. Now, if he picks any one of these red chocolates, the condition is satisfied. Right? So there are 10 different possibilities out of 20 possibilities. So this is 10 by 20. Right? Let's call this as the first pick. Now the second pick. Again, I'm asking him to pick a chocolate. Now what is the probability of my son again picking a red chocolate? Yes. Now let's see who will answer. I'm expecting a written question from you people, but let's see who all will get it correct. Okay. The people in YouTube, they're not responding. Well, you guys are very slow. You have to be quick. Okay. So there are two possible answers. Nobody has asked me a question. Vamsi asked me the question. Very good, Vamsi. Vamsi M. Wonderful. You should be asking me, did your son put the chocolate back into the jar or not? Did he eat it or did he put it back? Now there are two conditions, right? Maybe my son loves red chocolate. Sorry, blue chocolate. So he was looking for blue chocolate to consume. But when he picked it, he got a red chocolate. So what he would do? He would put the chocolate back. He would not eat it, right? So the conditions that we have to look at here is with replacement or without replacement. Now, if the chocolate has been put back into the jar, then I have all the 20 chocolates intact, isn't it? All the 20 chocolates are intact. So the probability of my son picking red chocolate in the second pick will also be same, 10 by 20 only. He did not eat it, he put it back. So he will have 10 by 20. Now, if I say without replacement, that means my son has taken the chocolate, he has consumed it. He has eaten it. Now there are two possibilities again. You might say 9 by 19. That's correct answer. 9 by 19 is the correct answer. But what if the first pick was a blue chocolate? This is when the first pick is red. But here, when the first pick, if it would have been blue, then what? If the first pick would have been blue chocolate, then in the jar you will have 19 chocolates only, because the first chocolate was consumed. It was not put back. But the red chocolates, all the red chocolates would have been there, right? So the answer would be 10 by 19 in this case. Isn't it? So we are looking at conditional probability here. When you say the two events are dependent on each other, if you say with replacement, then the first event and second event are not dependent. Second event has nothing to do with the first event, right? But without replacement, when you are trying to address this question, this particular problem, then the second pick result will always be depending on the output that we got in the first pick. Now, this is only a chance that we are measuring. It is not the output. It is the chance of the output. You have equal chance that you might get a blue chocolate also, right? We don't know what was the outcome. The second event will be depending on, the outcome of the second event will be depending completely or purely on the first event's output. This is called as conditional probability. Yep, this is called as conditional probability. Okay? Yes. Any questions in this? Because we are going to go for break now, and post the break we are going to discuss a concept called as probability distribution. If you are clear with probability concept, then we are looking at probability distribution. So probability is clear, right? Forget about conditional probability. Assume that we did not discuss it. Focus only on probability. Probability is equal to the number of interested events by total events, right? So we are going to further discuss on distribution of these probabilities. All right. So we'll take a short break now, and we'll come back and discuss about this. Right. So let's see how many of you have actually referring to YouTube channel. I see not many. Very less. Okay, 709 views. Okay, a little good. People have worked on over weekend. That's something that those views are telling me that at least few people have written back to read, go through the recording. It is there on Facebook and LinkedIn. Yeah, in the meantime, I want everyone to please complete yeah. All right, come back, complete the quiz in LinkedIn and Facebook. Make sure you're attempting this in the break time. All right, let's come back at 3 time. Very good. Nobody has actually utilized the brick. Okay, fine. Not interested. All right, so before the break, we were discussing about probability, which is nothing but number of interested events by the total events. That's your probability. Next, if I look at a single die, again, I'm rolling the die. I know that there are possible outcomes, right? What are those possible outcomes? I represent that as X, and I'm marking those values. So there are 6 possible outcomes. Then I'm rolling the die. Right? Now, I want to visualize this. I want to visualize these probabilities that each of the possible outcome has. If you calculate probability of X being small x, which would be any one of these values, we represent this as X is equals to small x. Small x could be any one of these. This is equal to interested events by probability, total events, right? 1 by 6. For 1, it is 1 by 6. For 2 also it is 1 by 6. For 3 also it is 1 by 6. For 4 also it is 1 by 6, 1 by 6, 1 by 6. So all the possible outcomes here have an equal opportunity. So what I'll do, I'll take the probability of the event, this experiment. 100% chance would be there for the outcome, right? But what is the individual chance? We don't know. So we are distributing that chance among the possible outcomes, and this is what you get. So if I take the data here, let me draw it here. I'm drawing it here. So this is my data. What is the data? X. What is X? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. So on x-axis, I'm marking my data. And I will try to mark the respective probabilities on y-axis. Here I'm marking the probabilities. If I do this, then the chance that 1 has is 1 by 6. How much does 2 has? 2 also has the same chance. 3 also has the same chance. 4 also has the same chance. 5 and 6 also have the same chance. So I'm marking like this. So this is 1 by 6. The probability of each and every possible outcome here is uniform. The chance is uniformly distributed. So we call this as uniform probability distribution. You're distributing the probability among the possible outcomes, right? How are you distributing it? Uniformly you're distributing it. So this is called as uniform probability distribution. Right. So this is one example. Let's talk about second example. Okay, this is example 1. Okay, let me erase this. And I will now talk about example 2. Let's take a data on x-axis. Okay, this is your x-axis, and here you are taking the data as heights of adults. Now you want to quantify adults, then you can say people who are between 20 to 40 years, okay? Across the world. Take each and every person across the globe who fits into this condition. And we are taking their heights, we are recording their heights. Entire population. When I say population, I'm talking about world. And y-axis, I'm trying to represent, here I'm trying to represent the probabilities. Okay, I'm marking probabilities. Now, what is the chance you have to find a person who is exactly 1 feet tall in the entire world? How much chance do you think you have in order to identify a person who is 1 feet tall? Yeah, what do you think? How much chance do you have? Yeah. Okay, people who are interested only in giving attendance and leaving, don't worry. You will get your attendance, you will get your certificate, okay? People who are seriously wanting to learn, please stay back. Don't ask me attendance link again. We will give you the attendance link. Focus here on what we are discussing. Yeah, friends. What is the chance that you find a person who is exactly 1 feet tall? Yeah. 1x, very, very less. 1, okay, 1 by total population, maybe 0, very good, okay. So can I represent that probability like this? Very less. I'm marking probabilities on y-axis, right? I'm putting it very less. Now, what is the chance that I have to find a person who is 2 feet tall? 1 feet is very little. What would happen to 2 feet tall person? A little more, right? A little more. So I will mark this like this. Similarly, I will be marking for 3 feet, 4 feet, 5 feet, 6 feet, 7 feet, 8 feet, 9 feet, so on and so forth. So for 3 feet, definitely it will be a little higher than 2 feet. 4 feet will definitely be a little higher than 3 feet. 5 feet would be like this somewhere here. 6 feet probably is something a little extra than 5 feet. Then if I look at 7 feet, then this is coming down, right? 8 feet will further come down. 9 feet will come down. 10 feet will be even less. Right? If I look into entire world's population, and if I theoretically look at the probabilities of me finding people who are respectively falling in these heights, then this is what I get, right? These are the bars that I'm gonna get. Right? Now, on this particular graph, if you look into this, can you tell me what all heights can I measure? What all heights can I measure? Okay, let me erase this. Yeah. what all possible heights can I measure? How many heights are there that I can measure? Yes, friends, what do you think? How many heights can I measure? Five to 7 feet, 5 feet, 6 feet, 5 feet. I'm marking so many 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I marked 10 values, right? But within these 10, I can measure a lot of heights, isn't it? So I might have 3.5, 3.6, or 5.5, 5.6, 5.8, 5.10. Yeah. So the answer to this question is infinity. I can measure infinite possible heights. How? If you look into these values, it's on x-axis, right? On x-axis, I can measure the numbers to any desired accuracies. For example, I can represent a 5 feet tall person as 5 feet. Exactly, I can say 5 feet. But I can also try and measure a person who is 5 feet 10 inches or 5 feet 1 inch. Or I can also measure a person who is 5 feet 1 inch, 2, 3, 9, 8, 5, 4, 3, 2. Here also I can say. This is also a valid height. This is also a valid height. If I go to a desired accuracy, 10 decimal values I want to measure, or 20 decimals accuracies, then I can measure those accuracies, right? So if I look into all those possible values that I can measure, then it is infinite. This type of data where you can measure infinite possible values is called as continuous data. So the range of heights is infinite that you can plot on this x-axis. So I can measure 0.00000001, so on and so forth. I can keep measuring, keep measuring, keep measuring for all those desired accuracies that I can measure, right? If I keep drawing that, keep drawing that, keep drawing that, and if I look at this complete diagram, then I would get a bell-shaped curve. Okay, I would get a bell-shaped curve. Yeah. So this is the distribution of probabilities for a random variable, which is represented as x, which is nothing but heights, under normal conditions. We are not even looking at abnormal conditions here. In the world, in regular conditions, if I have to try and find the heights of people, then this is the curve that I'm going to get. Right? The curve would be like this, right? The gray color that you're drawing, you're seeing, right? This would be your probabilities for all the possible values that you can draw on x-axis. So here you have to understand, if x is a random variable which is continuous in nature, that means it can be measured to any desired accuracies, then the range is going to be minus infinity to plus infinity. Theoretically, we are looking into heights, which is a positive entity, but we can measure any value which can be measured on a continuous scale will have a range of minus infinity to plus infinity. The second property, very interesting. Let's see how many of you will understand and answer this. What is the probability of me finding a person, let's say exactly 5 feet tall? Yeah, let's see who will answer this. I want to find a person who is exactly 5 feet tall. Can you justify? Very good, very good. Only 2 people responded. Wonderful, guys. That's not right, Edukondal. 0 is the answer. Denominator would be that, right? So probability definition is what? Interested events by total events, right? What is that you're interested here in finding out? You want the probability of a person who is 5 feet tall, exactly 5 feet tall. So on this entire scale, how many 5 feet will be there? Only 1. So your interested event is 1. But what is the total values that you have on x-axis? Infinite. So if you say 1 by infinity, it is always equals to 0. You'll not be able to divide, right, these values 1 into infinite pieces. That's not possible, right? You're saying 0. This is the second point that you need to remember, which says probability of any single value for these kind of variables where you can measure the data continuously will be 0. Now the third point, this is the property of probabilities. You're looking at properties of probabilities. Probability will always lie between 0 to 1, but what will be the summation of all the probabilities? What is the sum of all the probabilities? Sum of all the probabilities equal to 1, right? So if I try and apply that logic here, sum of all the probability values will be equal to 1. If I try and apply this logic here, then that's nothing but this shaded portion. This is the shaded portion that I get, right? Probability of right, each individual value is 0, but if you look into the sum of all the probabilities, then it is 1. So sum means what? You're basically doing what here? You're taking infinite lines like this. You keep drawing lines. When you keep drawing those infinite lines, you get this shaded portion. Sum of all these probabilities, we're talking about sum of all these probability, infinite probability values that you see, will be equal to 1. So I can also say area under the curve. Area is nothing but sum of all the lines, right? So area of this bell-shaped curve that you're seeing will be equal to 1. So these are the 3 properties that you have to remember, and these properties are actually explaining us the distribution of the data. What data? Distribution of a continuous random variable. The data is called as a random variable because they are randomly changing. We don't know, we don't have any control on the random variables. And if the random variable that we are looking at, if it is continuous in nature, continuous means you can measure to any desired accuracy, then such type of data will have distribution which follow these properties. And because we are collecting the data under normal conditions, statisticians have given a name to this which is called as normal distribution. And these are the characteristics of these normal distributions. Making sense, everyone? Are you able to understand the probability distribution concept here? Okay, wonderful. So if you recollect, just before this discussion, we were looking at the distribution of the probabilities for dice, right? We were looking at the distribution of a die, single die. And for that, you have seen this kind of a line. I mean, bar chart was what we were looking at, right? We were drawing a straight line and we were seeing the heights like this. Now for the die example, you cannot have any other value. You can have only these possible values. Fixed values were there. For the fixed values, probability calculation will be easy. 1 by total. I mean the desired events by total events. But here you cannot measure the probability. For any single value, you cannot measure the probability. Okay, that is a big challenge that we need to address with respect to continuous data that we are going to deal with. Yeah. This distribution that you are seeing is called as discrete probability distribution, because the data that we are looking at here is a fixed data. Fixed data means it is called as discrete data. It's called as discrete data. Whereas here the data is continuous. So we call this distribution, which is like a shaded portion of the curve, not bars. You don't get any bars here like this. You get shaded portion, right? This is called as continuous probability distribution. And whenever you look into any continuous data, by default, its distribution will look like this bell-shaped curve only. And these are the points that you have to recollect with respect to the distribution of the data. This one I have given a name, uniform probability distribution, because the distribution is uniformly distributed, right? The probabilities are uniformly distributed. So here under the bell-shaped curve, for this continuous data, we call this as normal probability distribution. This is just a name which is given, okay? Why normal? Because statisticians, right, came up with these kind of study. I mean, the bell-shaped curve for all the data points which were being collected in normal conditions. There's no abnormality in this particular data. Okay? So probability distribution can broadly be classified into two types. Sorry, my bad. On y-axis, we'll always plot the probability values. On x-axis, we'll have data. But this data can be classified broadly into continuous data and discrete data. And based on that data, we have continuous probability distribution and discrete probability distribution, right? Based on the data. Now, if you have a discrete data, then coming up with histogram or bar plot will tell us about the probability distribution. It will clearly explain us the probability distribution. But what if you have a continuous data? What if we have a continuous data? Yeah. So we'll not be able to see that properly, right? So let me load the data here. Where is data? Yeah, data of cars. So here I'm looking at cars data. I have these values, 50 entries are there. I'm also looking at Titanic data here, okay? And it has right character data here. Now I'm coming up with visualizations. I can simply say right? I can simply calculate bar plot. It is talking about distribution of the data only, right? I can also say histogram, which will give us even better picture of the probability distributions, right? So you can see the shape. But because I have discrete data now, what is the discrete data? 0 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25. So I'm discretizing the data here to come up with histogram. But what if you have to come up with a continuous visualization? For example, speed here is a continuous data, right? So here we have a function or a visualization technique called as density plot. And in order to get the density plot, we have to use a library called using R. So I'm installing this library called using using R. Okay. Now using this, I'm coming up with visualization. So this is one way to come up with a visualization of the bell-shaped curve. Plot density of this. If I just select this and execute, then this is giving us the calculation, density calculation. Density is nothing but area, shaded portion, right? So I'm coming up with a plot on top of that density calculation, and you see this is the bell-shaped curve that you get. You can also come up with the same visualization or similar visualization using this library called using R. This using R library or package gives us the density plot function. So if you say question mark of this density plot, it is under using R, and it allows one to compare empirical densities of different distributions in a simple manner. So you just execute it, and you can see it is calculating this density. Density plot comes in two flavors. One is the uppercase D, the other one is the lowercase d. Okay, and this density plot with lowercase d is part of another package called Lattice. Lattice is a dependent package which is required for using R. So automatically that lattice is also given. And if you plot this, this is the visualization that we have. And these circles are basically pointing to the number of data points that we have. And this is the shape of the curve that we see. Now you can see that there is a bell-shaped curve. Now the shape statistics is something that we discussed. Remember, we completed shape statistics, right? We looked at histograms, then we also discussed about box plots. Now we are looking at density plot, different types of density plots, distribution concept, probability distribution. We write in short as ND, normal distribution. It has specific properties and all that, right? So this is about your shape distribution. But if you look into these shapes, different values, I mean different data will give us different shapes. So if I do the same three calculations with respect to distance, Look at that shape. It changed, right? Changed. But all these visualizations that we are seeing will have the bell-shaped curve. But these bell shapes will vary. So the point that I'm trying to bring in is the characteristics of this normal distribution is explained by two important parameters. The first one is mean. The first one is mean. Mean is the value which is the most popular one or most repeated one, right? Or the representative value. So the peak of your visualization here will represent mean. Majority of the data is falling there, right? So your center would be that. Right? So mean is represented by the peak of the visualization, bell-shaped curve. But you can also try and understand the second moment business decision. This is first moment, which is talking about measures of central tendency. The second moment talks about spread of the data, right, from the center, right? So that is your standard deviation or variance. Now that is given by sigma, right? This is spread or standard deviation. So centrality is being talked about the first moment. The width of the bell-shaped curve is being spoken about by variance or standard deviation, the spread. So these are the two important characteristics of the distribution of the data. So we say X, if it is a random variable, then it is distributed normally using mu and sigma. This is the representation for the distribution of the data. Right? And then there are a number of different visualizations that you're seeing here, right? So if I come up with density plot of this data, it's like this. If I try and come up with density plot of Titanic dollar, let's say frequency. Okay, I have to convert the Titanic. I'll have to convert this as data dot free. Yeah. Now if I say Titanic $1 frequency, it's a continuous data. Frequency is a continuous data, right? Look at that. So this is one visualization. This is another visualization. This is another visualization. So for each and every data point that we see, the variable that we are seeing, it will have a different shape, right? Those shapes are characterized by these two parameters, mu and sigma. Yeah, mu and sigma. So out of all this, three visualizations that we have seen, this is 1, this is 2, this is 3. Out of these three visualizations, which visualization is actually following those properties that we discussed? The normal distribution properties. The value should basically be continuous. That means the value should have minus infinity to plus infinity range. At least theoretically, they should satisfy that condition, right? Then area of any single value should be equal to 0. Probability of any single value will be equal to 0. and sum of all the probabilities will be equal to 1, that is area under the curve is 1. And if I split my data at the center, it should be symmetrical in nature. Bell-shaped curve is symmetry, right? This is not symmetry, forget about this. This may be symmetry. This is also not symmetry. So among three, this one looks a little symmetrical in nature, right? Yep. This one looks like a symmetrical curve. Now, given so many different options, different variables that are possible, how do we identify which variable will actually follow the properties? This will be a trick, right? So statisticians have said, let us take a fixed standard distribution, fixed defined properties, and call that as a reference, use that as a reference. And this fixed defined properties will have standard, we're calling it as a standard reference, right? It will become a reference. So standard normal distribution, right? And we called this variable as a z. To represent that it is standard, we represented the variable as a z. And the properties that z will have is that it will be distributed normally, but with respect to mu as mean and 1 as the standard deviation. Yep, so that's your z, which is known as standard random variable, standard continuous random variable, which is the standard. So that's your z, right? So if you have these properties, then it is referred as a standard. And this standard will always have a perfect symmetrical bell-shaped curve. It's a perfect shape. Yeah, I'll not be able to draw such a perfect bell-shaped curve, but z will have a perfect bell-shaped curve, which is distributing the center equally. Yeah, it will distribute the center exactly the center. Right? So that is your z distribution. Now you might ask, hey, why are we learning all this? We are learning all this to do two things. One is to understand that the data will always follow a normal distribution. Any continuous value, by default, we assume that it follows normal conditions. And based on these normal conditions and normal distributions, a lot of statistical calculations are defined. A lot of calculations are defined based on this. So we are verifying whether the variable is actually following normal distribution or not. That verification is done using something called as normal QQ plot. Okay, we'll discuss this in detail tomorrow. We'll start with normal QQ plot. This normal QQ plot is comparing your random variable x with the standard variable called z. You're comparing it. And if x is similar to z, the distribution of x is similar to distribution of z, then we can also say x is normally distributed. Right? So that is interpreted using normal QQ plot. It's a visualization. But this visualization will help us interpret whether the data is normally distributed or not. Yep. So that's your normal QQ plot. Then we will also discuss about something called as transformations. And then we'll also discuss about standardization and normalization. Why we use this, how do we calculate this, right? All those things we will cover in tomorrow's class. So today's class we focused only on normal distribution. Probability distribution, and this probability distribution can be measured as discrete probability distribution, and then we also have continuous probability distribution, and this is based on the data for which we are measuring the probability for. So we are measuring the spread of the probabilities, which is nothing but spread of the chances, right? Which value has more chance, which value has less chance. We are trying to do that. We are identifying that, right? So under the continuous normal distribution, we discussed about the default distribution technique, which is called as normal distribution, and the three properties. Range of x will always lie from minus infinity to plus infinity. The second one is talking about probability of any single value is going to give you a result as 0. And the third one is sum of the probabilities will be equal to 1, which is nothing but area under the bell curve will be equal to 1. An additional property that you need to look at is the bell-shaped curve will be symmetrical. If it is symmetrical, then the area is divided exactly to half from the center. But what is that center? That's your fifth property. Here mean will be your center, which will be equal to median and which will be equal to mode. Mean will be equal to median will be equal to mode. Right? So these are the 5 things that you have to by heart. All right. Then in R today we are seeing density plot. How do we visualize this bell-shaped curve? And here we can do plot function. We can do density with capital D, density with smaller d. Right. Any questions? Let me see your questions now. Yeah, you have the attendance link, feedback link, right? Please fill in up and let me also take your questions. Data science mind map. It's there on the website. This is the website. 360DigiTMG. You log into this and you click on mind map. It will redirect you to the mind map. And here you will have a drop down. Click on the first one, or based on whatever you want to see, click on that respective mind map. And if you click on it, it will open. And double click on these will expand. No questions? Okay. Now we have till one more week, right? This week and yeah, next week. Lakshmi Bala. Yeah. Z is a standard Varun which follows certain properties. We will discuss that tomorrow again. I'll detailedly explain that again tomorrow. Z is a standard. Like how you have X, we have Z. Random variable is just a representation. But it has certain properties, unlike your random variable X. Attendance link has been pinged, Sai. You can scroll down the link, chat window, you can see the attendance link. In the sticky pad also you have the attendance link. You can click on that. Okay, it's there on the sticky note, right? In the chat window, just above your chat window, the sticky note is there. Hey, thank you. All right, thank you. Yeah, thank you all. Avinash SD is the function. For standard deviation, you're going to say SD. SD. Smaller case, both are smaller case, and you have to pass your data here. You want to refer to the R programming videos on YouTube channel to get all those calculations done. Yeah. All right. Any more questions, anyone? I'm typing the link, right? I've measured, pinged the link also. Yeah, Priyanka, thank you, Priyanka. Priyanka also pinged the link. Hey, all right, friends. Thank you so much. We'll connect tomorrow. Take care. Bye.